Hi, it's Mads again and welcome to the new episode of our video lesson for today. The title of this lesson is about projectile motion, also known as two-dimensional motion. Before we proceed to the deeper understanding of this matter, let us have our main objective. At the end of this lesson, you are expected to describe the projectile motion along the horizontal and vertical components. So let's try to understand what is projectile motion. Projectile motion is simply the motion of an object that follows a path. That means, for example, considering this diagram here, we have here a football. Assume that this football is being kicked by a kicker player with a certain angle of, let us say, theta above horizontal line, and this covers an initial velocity as it moves to the air. And as the kicker player kicks the ball, this will follow a certain path, but we cannot see that using our naked eye. But in this diagram, assume that the blue line here is the path covered by the ball as it returns to the ground. Now, this blue line here now is what we call the trajectory line. This trajectory line is the exact meaning of the word path in this definition here. Looking at this diagram, we can extract more information from this illustration. But before we proceed to that, let us try to understand first that in projectile motion, we are considering both the x component and the y component of this motion. That means that I can put here initial velocity along y-axis and initial velocity along x-axis. So for example, the ball moves at this point. The velocity of the ball here, as the ball moves along y component, it gradually changing. It can be decreasing or increasing. But the bottom line is, along y component, the velocity of the ball is changing. So for example, we have here the velocity. The velocity here is still the with respect to the velocity at x-axis and also velocity at y-axis. And as the ball moves closer and closer to the maximum height, let us say this one is the maximum height or big letter H, maximum height of this path, the velocity along y component of the ball at the maximum height is equals to 0. So I can label this one, this path here as my maximum height, or it can also be written as y sub max, or some physics book refers this as a small letter h, something like that. But either of that is correct. So at the maximum height, b sub y is 0, and until it reaches to the ground, the velocity still is b, and we have also still velocity along x-axis and velocity along y-axis. And also in this one, the final velocity here can also be written as like this, b sub x, and still we have b sub y component. So as you can see, the ball changes from original position, let's say position A, into position B. That means that there is a change in displacement, and this displacement now along x-axis is what we call the range of this projectile motion. So we can write here as range or big letter R. Now I just want to prove that before we proceed to the equations for this diagram, I just want you to see the justification why the b sub y here is 0 using our PET simulator. So going to our PET simulator here, assuming that we have here a cannonball, never mind the initial speed, but we have here a cannonball, and we'll try to observe the velocity of this cannonball as it travels from point A to the final position here, or for let us say point B. So as I press this one, The green line here is the velocity of the object, the component velocity of this cannonball. Horizontal line here associated with the horizontal velocity of the cannonball. So you try to observe. Okay, so this is the maximum height that we have here, marked as I think color green. Now let's try to observe. Let's try to observe another cannonball, and I will post it. As you can see, as the cannonball move closer and closer to the maximum height here, the length of this vector line here, or the vertical line here, is getting smaller and smaller until it reaches to the maximum height, wherein the velocity there is 0. And try to observe, and I will post it. So as you can see, the vertical line here is now becomes 0 now. That means that the velocity along y component is 0. So that is the justification why this velocity at maximum height is 0. We can start from x-axis, and also we can separate the concept from x-axis and also from y-axis. Along horizontal line, the acceleration here, which is given by a sub x, is equals to 0, because the velocity of the object along x-axis is constant. If the velocity is constant, this means that the velocity is not changing along this course. Meaning to say, if velocity is not changing, the acceleration is 0. But in y-axis, the acceleration here is given by a sub y. This is exactly equals to the acceleration due to gravity, which is 9.8 meters per second squared. Meaning to say, the acceleration of this ball along y component is exactly the acceleration of the, or acceleration due to gravity, which is given by 9.8 meters per second squared. And before I forget, since the ball is moving, that means this is moving with respect to time. So we have also here, we can also write here time up. I can put time up here, or in some other book, we call this one as time flight or time of flight. And if we have a time of flight here, we have also what we call time down. I can write here, or time of fall. But take note that time up or time of fall, I mean time of flight, sorry, time of flight is just be equals to time of fall. Meaning to say, if the time of flight is 1 second, also the time of fall is 1 second. But the total time, or t sub tot, is given by 2 times small letter t. Sorry. So this is now the another information that we have taken from this diagram. And let's move on to the initial velocity along x-axis. So to solve for initial velocity along x-axis, let's put here, solve for initial velocity along x-axis, because we cannot describe alone the initial velocity here without considering the x and y component. So to describe the velocity of this object, let's try to first deal with the x component and the y component of that velocity. So the first thing is to solve for v sub ix. In solving for v sub ix, as you can see here, if we have to enlarge this one, this line here, we have a vertical component and also we have a horizontal component. So if we have to draw here, this will be our vertical component and this is our horizontal component. We will label as x and this one as y, and assuming that this is the ball being kicked by the kicker player with an initial velocity of the angle above horizontal line. Now to solve for the initial velocity along x-axis, we will use the aid of the basic trigonometric function. Now take note that this is b sub ix and this is b sub iy. So this b sub iy here is just b equals to the b sub iy here. So I will use the cosine function in solving for this one. So cosine theta is given by adjacent, which is b sub ix, divided by the hypotenuse, which is b sub I. You cross multiply that, this is equals to b sub ix is equals to b sub I cosine theta. And this is now the formula for finding the initial velocity along x-axis. And we can write here initial velocity at x-axis. Moving on, solve for the, let's solve for y, b sub iy, initial velocity along y component, and still we can use this diagram here. So this is our y and this is our x. This is the path of our football with an initial velocity at certain angle. So this is b sub iy and this is b sub ix. So as I said here in this diagram here, the b sub I here, b sub iy here is just be equal to the b sub iy here. So this is equals to b sub iy. So to solve for the initial velocity along y component, we will use the aid of, again, trigonometric function in the form of sine function, or sine theta is equals to adjacent, opposite, I mean. The opposite of that is b sub iy divided by this b sub I here. You cross multiply that, this becomes b sub iy equals to b sub I sine of theta. And this is now exactly the formula in finding the initial velocity along y component. So we have already extracted the formula for solving initial velocity along x-axis and y-axis. Now let's move on. X-axis, and let's put here y-axis. Now in solving for the unknown variables that we'll be encountering as we go along in our problem in projectile motion, we can use the kinematics equation. As you can still remember, we have 5 kinematics equations, but in this case we're just only using 2 equations there. The first one is the equation for final velocity, which is given by this one. B sub f is equals to b sub I plus a times t. And this is one. The second equation that we're going to use is x position equation. X is equals to b sub I times t plus 1/2 at square. And if we translate that into y component, this becomes b sub f is equals to b sub I minus g times t. And for number 2 here, this equals to y is equals to b sub I t. This is negative, not positive. Since the velocity, since the acceleration due to gravity along y component is equals to negative g 1/2 gt square. Let's try to use this one, this equation here. So this is equals to this final velocity here becomes b sub y. B sub y is equals to b sub ix plus a times t. Now as we have said here that in x-axis acceleration is equals to 0. So we can assume that this term here is equals to 0, leaving us the equation of b sub, sorry, that's not a b sub y. This is b sub x. That's a b sub x. B sub x. So this is b sub x is equals to b sub I x. This equation now, this equation here, b sub ix is equals to b sub ix justify this concept here, which is the velocity in x-axis is constant, not changing. That means that whatever the value of initial velocity here, that's gonna be equals to the value of the b sub ix here, which is also equals to the b sub ix from this equation here. So that's the meaning of this equation here. Moving on to this equation here, the position equation. Let's try to use that and try to observe if what would be the equation that we might get from this position equation. So this is equals to x is equals to b sub ix times t plus 1/2 at square, since acceleration is equals to 0 along x-axis, and we can cancel out this one. We can assume that this is all equals to 0. So this is equals to x is equals to b sub I x times t. And this expression here now is the expression or the formula that can be used for finding the displacement of that ball, of that object moving in a projectile motion along x-axis. Okay, but take note that this x is equals to b sub ix times t can also be used to find the range of the projectile motion. That means that I can also assume that x here is just b equals to the range. Okay, let's go back to that later. So we have here now another equation, which is an equation for displacement in finding the displacement of the object along x-axis. Now let's go for y-axis. So let's try to use this one, this equation here. This is becomes the b sub f there becomes b sub y equals to b sub iy minus g times t. Okay, now b sub y here, let's try to recall that b sub y here is equals to b sub I sine of theta, as we have computed or derived from this equation here. So b sub iy is equals to b sub I sine theta. That means that I can also substitute b sub y is equals to b sub I sine theta minus g times t. Now in this diagram, we also said here that the y velocity or the velocity along y component at maximum height is equals to 0. That means that b sub y here can be assumed to be 0. So this becomes, the equation here becomes 0 is equals to b sub I sine theta minus g times t. And we can rearrange this equation in terms of t. So this becomes b sub I sine theta equals to g times t. This is divided by g. So this give us the equation of time is equals to b sub I sine theta over g. Now as you can see, we have again another equation here. This equation here now is the equation. I can say that this equation can be the equation for time of flight, or can be equation for time of fall, since t up is just b equals to t down. So we can use this one in finding the time interval or time flight of the object, or time of fall of the object. So we have another equation. Now let's try to use this equation again, this one. So y here is equals to h, or just b equals to the y max. So h is equals to b sub iy times t minus 1/2 g times t square. Now remember that b sub iy is equals to this one. So let's try to bring this one here. So this is equals to h is equals to b sub iy t minus 1/2 gt square, and this is equals to b sub iy here is equals to b sine theta. So this is bi sine theta times t minus 1/2 gt square. So this is equals to b sine theta. Time here is equals to this one. So this is equals to, instead of using time, we'll substitute the value of time here. So this is equals to b sine theta over g minus 1/2 g. Now time here is also equivalent to time there. So this is equals to b sine theta over g. This is all over squared. So this is equals to, we multiply this one to that term here. So this is a b sub I square sine times sine is sine square theta divided by g minus 1/2 g. B sub I square is b sub I square. Sine theta square is equals to sine square theta. G times g is g square. And this is equals to, this is cancel out to the other g here. So this is cancel out to this one. And this becomes b sub I square sine square theta is divided by g minus 1/2 equals to b sub I square times sine square theta divided by g. So this is equals to, I want you to treat this one as one term. This is, you treat this term here as a. For example, this is a. And this term here is also a. This is, this becomes, if we want to put here, okay, this is equals to a minus, you get this one 1/2, and this is pair of that, this is a minus 1/2 a. So something like that for you to visualize the problem. So this is equals to a minus 1/2. We have a coefficient here of 1, so this will give us positive 1/2 a. That means if we subtract this one, b sub I square sine theta divided by g minus 1/2 times b sub I square sine theta square sine square theta divided by g will give us positive 1/2 b sine square theta over g, as what we have explained in this section here. So meaning to say, this becomes, I will move it here. So this is equals to 1/2 b sub I square times sine square theta divided by g. And this is equals to 1 multiplied to this term here. This becomes b sub I square sine square theta divided by this one to multiply to that. So this is 2g. And this is our maximum height. So to solve for maximum height, we're going to consider this equation, and I will label this as maximum height. So this will be the equation for maximum height. This is G. Okay, now moving on to that, since we said here that x is equals to r, that means that x is equals to v sub I x times t. This means that we can also use this equation in solving for range, or just b equals to range is equals to v sub I x times t. But the difference is range is will be using the total time, since we're focusing more on the entire trip of this projectile object. So if that means if we have to consider total time, we are going to consider the initial position and the final position of this object. So from the initial position to final position, what would be the time here? Now obviously the time here is the total time of the entire trip, or interval of the entire trip. That means that this will be equals to r is equals to b sub I x times 2t. So this is now the basis for deriving equation for the range of the projectile object. Now using this equation, solve for range with the formula of r is equals to b sub I x times 2 times t. From this equation here, this one, so this becomes, since b sub I x is equals to b sub I cosine theta, so this is equals to b sub I becomes b sub I cosine of theta times 2. Time here is equals to this one, this term here, as you can see here. So this is equals to initial velocity sine of theta all over g. So we will substitute this value to the value of time here, so that we can eliminate the variable t here. So this is equals to b sub I sine theta divided by g, and this is equals to you multiply this one, b sub I to multiply this term here, this is a b sub I square, this is sine theta cosine theta all over g. So let's try to recheck. B sub I times b sub I is b sub I square. Cosine times cosine theta is equals to sine theta cosine theta. Copy the 2 here, so it becomes like this one. Okay, and next one is we're going to simplify this equation. So as you can see here, this term here has an equivalent trigonometric identities. We call this one as function of twice angle. This is function of twice angle. You can anyway, you can read this one, function of twice angle, and you can read this concept of function of twice angle from the book of Paul. I will put here Paul R. Ryder, or Ryder, I think Ryder. The title of the book is Plane and Spherical Trigonometry. If you have the book, or if you have the access of the book of Paul Ryder, that's you can read that at I think page 128. Try to recheck that function of twice angle. The function of twice angle states there that 2 sine theta cosine theta has a trigonometric identities of, the trigonometric identities of that is 2 sine theta cosine theta is equals to sine of 2 theta. So from that, we can write as b sub I square times sine 2 theta divided by g. And this is now the formula for our for computing or for solving for the range of the projectile. So this is now the formula for the range of the triangle. Now moving on to that, if we have to combine the equation for the displacement of x, combine, or the term is substitute, should I say? If we have to substitute the x-axis displacement equation into y-axis displacement equation by eliminating the time, we can get the formula for trajectory path, this one. So let's try to solve for the trajectory path or trajectory equation by simply combining the equation for x-axis displacement and y-axis displacement. For the x-axis displacement, we have this equation here. This is the equation for x-axis displacement, and for y-axis displacement, we can use this one, this term here for y-axis displacement. So let's try to solve for that. So for x-axis, this is given by x is equals to b sub I x times t, and for y-axis, this is given by y is equals to b sub I y times t minus 1/2 g t square. So this is equals to x here is equals to b sub I cosine of theta times t, and we will solve this one in terms of t so that we can eliminate time here. So this becomes b sub I cosine of theta divided by b sub I cosine of theta, and this is cancel out. So this will give us t is equals to x over b sub I cosine of theta. That means all the value of time, all the variable time here will be replaced to this equation here or term here. So this is equals to solve for trajectory path. This is equals to y is equals to b sub y here is equals to b sub I sine of theta. So we will substitute that. This is b sub I sine theta times the time here is equals to x over b cosine of theta minus 1/2 g. Time here is again x over b sub I cosine of theta square. So this is equals to this term here, it will be cancelled out to this one, and sine theta divided by cosine theta, let's try to have this one here, sine theta divided by cosine theta is equals to, sine theta is, if this is the right triangle, this is, shall we say this is y and this is x, and this is, let us say, this is z for that instant. And this is equals to, for sine theta, this is equals to opposite, opposite over z. So opposite over z divided by, for cosine, adjacent divided by hypotenuse over z. So this is equals to y over z times this one. It will be reciprocal to the x. So this is z over x, cancel out. So this becomes y over x. Y over x now, the term y over x now here is equals to, the x here is the adjacent, and then the y here is the opposite. So opposite divided by adjacent is the term TOA. This is opposite and this is adjacent. This means that the y over x is tangent theta. That means that sine theta divided by cosine theta is equals to tangent theta. So we will put here, we will write here tangent theta equals tangent theta times x minus, this is 1/2 g times x squared divided by b sub I squared, cosine squared theta, close. So you multiply this one into that, and also g to that, and 2 is for the denominator. You multiply the denominator 2 into the denominator here. So this is equals to tangent theta x is minus, this is 1 times g times x squared is equals to g x squared divided by 2 times bi squared cosine squared theta is equals to b sub I squared cosine squared theta. And this is now the equation for the trajectory path. So we can write here trajectory equation. Okay, so for final velocity of the projectile motion, considering this diagram here, for example, we have here the final velocity, and we are going to find the final velocity after hitting the ground or before hitting the ground. We will just use the Pythagorean theorem, because if we have to draw that, if this is the path of the ball, so this is our vertical component. This is the vertical component, and this is the b sub x, this is the b sub y. This will be our final velocity, and we can solve this one using Pythagorean theorem. You can do this by solving for or applying Pythagorean theorem. So this is equals to, final velocity is equals to square root of, this is b sub x square plus b sub y square. And take note that the b sub x here is just b equals to b sub I x, which is equals to initial velocity, but b sub I x is equals to b sub I cosine theta. That means that if you have the initial velocity, or if you have the value of b sub I x, we can use that as the value of b sub I x to be substituted in this equation here. But for b sub y square, or for b sub y is equals to b sub f for the kinematics, since this is already at hitting the ground, so we can solve that by simply using this equation here. B sub f is or b sub fy is equals to b sub I y minus 2gy square, and this is equals to b sub y square root of b sub I y squared minus 2gy, which is b sub I y here is equals to b sub I sine theta minus 2gy. So if the value here that can be taken from this equation will be substituted to the value of b sub y here, and you can now get the final velocity of the projectile motion. So we can label this one as a final velocity. So this will now the equation for final velocity. Now to sum up this one, we will try to summarize our equations here. So all of the velocities here that we have here, the SI unit for that is meter per second, and the range here is meter. So as to the displacement here, which is also meter, and this one is also SI unit for this one is S. So these are now the formulas that we need to memorize or we need to know when it comes to projectile motion. So you are free to comment on our comment section if you have some clarifications regarding this discussion. Thank you so much, and see you in the next video.